7.2 Antidifferentiation by Substitution. Definition: indefinite integral. The family of all antiderivatives of a function f of x is the indefinite integral of f with respect to x and is denoted by the integral of f of x. If f is any function such that the derivative is equal to the function f, then the integral equals f of x plus c, where c is an arbitrary constant called the constant of integration. And really all this is saying is when you integrate, and you aren't integrating, let's say, from -2 to 3, if you just have the integral of, let's say, x dx, then the answer on this one would be 1/2 x squared and then plus c. You have to have plus the constant when you're doing what's called an indefinite integral. This is the definite integral. Evaluating an indefinite integral. Evaluate. We have 1/3 x to the third, and then plus cosine of x and plus c. Now, if we took the derivative of this, we would get x squared, we would get minus sine, and then the derivative of the constant would be 0. Verify antiderivative formulas. Verify the antiderivative formulas. They're saying that the integral of u to the -1, well, that's equal to 1 over u, and they're saying that the answer is natural log of u plus c. To verify that this is true, we'll take the derivative of this piece right here. The derivative of natural log is 1 over u, and the derivative of c is 0, and that can be written as u to the -1. So when we do the derivative of the answer, we get right back to the original. On letter B, let's start by taking the derivative of this and see if we can get back to just the natural log of u. We have first times the derivative of the second, plus the second times the derivative of the first, and then the derivative of negative u is -1, and the derivative of c is 0. The u's cancel. We have 1 plus natural log of u times 1, which is still natural log of u, then -1, and finally we get natural log of u. Paying attention to the differential. In example 3, we have let f of x equal x to the third plus 1, and let u equal x squared. Find each of the following antiderivatives in terms of x. We have the integral of f of x dx, so we want to integrate with respect to x, and we have f of x. It's right there. So we're doing the integral of x to the third plus 1, but with respect to x, which will be 1/4 x to the fourth plus x, and then plus c, because this is an indefinite integral. On letter B, we have the integral of f of u with respect to u. So let's plug u into f of x. We get u to the third plus 1. We have the integral of u to the third plus 1 du, which is 1/4 u to the fourth plus u, and then plus c. Then on the last one, we have f of u, but it's with respect to x. So when we plug u into this function, we're actually plugging x squared into this function. So we have the integral of x to the sixth plus 1 dx. Now that's 1/7 x to the seventh plus x plus c. Example 4, using substitution. Evaluate the integral of sine of x e to the cosine x dx. We're going to let u equal the cosine of x because we have the derivative of cosine in this problem, which is sine of x. Now if we take the derivative of both sides, we get du equals negative sine of x dx. So there's the derivative of both sides. Now we have a sine of x dx, but we don't have that negative. So let's divide the negative over. We have negative du is equal to sine of x dx. We have the integral of, first of all, it's going to be negative because we're going to replace sine of x dx with negative du. So negative du, and now we replace cosine with u in this formula right here. So we have e to the u. Now the antiderivative of e is e, so we have negative e to the u plus c. We didn't start with u's, so we can't end with u's. We have negative e raised to the cosine of x, and then plus c. Example 5, using substitution. We want to look for a function and its derivative, and we want to let u, let's let u equal as much as possible, but we want to let u equal the function so that when we take the derivative, we have a multiple of the derivative. So we're going to let u equal 5 plus 2x to the third, because when we take the derivative, we get 6x squared dx. Now we have the x squared dx. We have this much right here, but we don't have that 6 in the problem, which is not an issue because we can divide by 6. So we have 1/6 du is equal to x squared dx. So we can replace x squared dx now with 1/6 du. So we have 1/6 integral. We put the du on the end, and now instead of the square root of all this, we have the square root of u. Well, that's u to the 1/2, so we're going to add 1, which is u to the 3/2, but then times 2/3. And that 1/6 is just going to follow the problem along. And then, of course, plus c. So finally, we get 1/9 times the square root of u, but we didn't start with u, so we can't end with u. We have 5 plus 2x to the third raised to the third power, and then plus c. On this one, we don't have a function and its derivative, but I can change this to the integral of cosine of 7x over the sine of 7x dx. And now we can let u equal sine of 7x, and du now is equal to 7 cosine of 7x dx. Well, I have the cosine of 7x dx, but we don't have the 7 sitting out front, so we're going to have to divide both sides by 7 before we actually do the substitution. We have 1/7 du is equal to cosine of 7x dx. I can replace the cosine of 7x dx with 1/7 du. Let's do that. 1/7, we put the du on the end. And then I've gotten rid of this and this. Now I have 1 over u. 1 over u. The integral of 1 over u is the natural log of the absolute value of u. But u is sine of 7x. And then we have plus c. Now that's the answer. Let's take the derivative of this and try to get back to the original. If we took the derivative, the outside function would be natural log. So we have 1/7 times 1 over sine of 7x. The next function would be sine. The derivative of that is cosine of 7x. And finally, the inside function would be 7x, so we multiply by 7. Now those would cancel out. We'd get right back to cosine of 7x over sine x, which is cotangent of 7x. Example 7, setting up a substitution with trig identity. Find the indefinite integrals. In each case, you can use a trig identity to set up a substitution. Let's look at the first one. We have 1 over cosine squared of 2x. Now that is the same as, let's see, the reciprocal of cosine is secant. So we have secant squared of 2x. Well, the antiderivative of secant squared is tangent of 2x, but if I took the derivative of this, I'd have times 2. So we need a 1/2 tangent of 2x plus c. On this one, it says cotangent squared of 3x. Well, we don't know the antiderivative of cotangent, so let's change this. If I had sine squared x plus cosine squared x, that's equal to 1, and I would need a cotangent. That's cosine over sine. So let's divide everybody by sine squared. We have 1 plus cotangent squared x is equal to, this would be cosecant squared x. So cotangent is equal to cosecant squared minus 1. So now we can change this to cosecant squared of 3x minus 1, because we have this 3x here. Well, the antiderivative of cosecant is negative cotangent, not squared. The antiderivative of cosecant squared is negative cotangent of 3x. If I took the derivative of this, I'd have a 3 out in front. We don't have that. So we need to balance that out with a 1/3. And then we have minus x. And then plus c. With example C, we can change cosine to the third into cosine squared x times cosine x. And then we can change cosine squared into 1 minus sine squared x times cosine of x. And then we can let u equal sine of x. That way du is equal to cosine x dx. And we have cosine x dx. Now this turns into 1 minus u squared du. Now the u is sine, this would be u squared. The integral is u minus 1/3 u to the third plus c. We didn't start with u's, we can't end with u's. So we have u is sine. So we have sine of x minus 1/3 sine to the third x, and then plus c. Evaluate a definite integral by substitution. Let's let u equal the function, which is tangent of x. That way when we take the derivative, we have the secant squared x dx. Now we can replace secant squared x dx with du, and tangent gets replaced with u. So now we have the integral of, let's see, u times du. Now we can change the limits also. U is equal to the tangent of x, and these are really x's, from x equals 0 to x equals pi over 3. But now we want to change them to u's. Well, u is equal to the tangent of 0, and the tangent of 0 is actually 0, so this 0 for x becomes 0 for u, and then on the top one, the pi over 3, that u is the tangent of pi over 3. Let's see, pi over 3, we have 1/2 square root of 3 over 2. Tangent is sine over cosine, so now u equals the square root of 3. So what was pi over 3 for the x is now the square root of 3 for the u. And we have 1/2 u squared, and we're evaluating from 0 to the square root of 3, which is equal to 1/2 times, well, the square root of 3 squared is 3, and then minus 0. So our final answer is 3/2.